Hello everyone, welcome to this course on discrete mathematics, and now we are still in this topic of countings. Especially today we are going to discuss about this permutation and combinations. It's basically about the possibility trees and multiplication rule that we have seen in the last lecture, but today we are going to talk more about the probability based system. Before we go on, let's talk about what is called a pigeonhole principle. It's one of the interesting principle that's there. For example, suppose a flock of pigeon flies into a set of pigeonholes to roost. If there is more pigeon than pigeonhole, then there must be at least one pigeonhole that has more than one pigeon in it. Just imagine that you have a set of pigeonholes, and suppose you have like 11 pigeons coming in. What happens? Like each pigeon goes to the, okay, let's say I have already 12 boxes, so let's say we have 13 pigeons coming in, 7, 8, 9, 10, 11, 12. So 12 pigeons, they already in the hole, they already have some spot where they can be, but the 13th pigeon does not have a place to stay. So what happens is that maybe 13th pigeon would go into some space, so that at least one pigeonhole has more than one pigeon. That is the basic idea. Let's talk more of it. If k plus 1 or more objects are placed into k boxes, then there is at least one box that contains two or more of the objects. The same idea that has been explained with respect to k boxes here and objects. Let's talk more on this principle. Say you have in a group of 367 people, there must be two people with the same birthday, isn't it? Because you have 367 people, and the maximum birthday could be like 366. Even if you take the leap year, you might have 366 possibilities of birthdays, which means that at least two persons has the same birthday. Likewise, in a group of say 27 English word, at least two words must start with the same letter. Do you agree that? Yeah, of course, right? Because we are talking about a group of 27 English words. So it can be any words, like it can be ant, bat, cat. So we are talking about English words A, B, C, D. It goes on till Z, say for example. So you got 26 already, but in a group of 27 words, so you should have another one word that might be repeated. Yes, at least two words must start with the same letter. That's right. Maybe at least, say for example, you might have another. We already have ant, bat, cat, so at least one of those words should be of say for example, in this example we have C is being repeated twice. Yeah. In generalized pigeonhole principle, if n objects are placed into k boxes, then there is at least one box containing n by k objects. So this is the theorem 2 for this principle. Let's talk about more in details, like among 100 people, there are at least 100 by 12, that is 9, born on the same month out of 100 people. So how many students in a class must there be to ensure 6 students get the same grade? 6 students must get the same grade. So you can think about the possible combinations which would yield 6 persons to get the same grade. So you can think about the previous things, the boxes or grades. Let's say k equals 5, then n by 5 is 6. So you have to trying to find what is n. N is going to be the number of students in the class. So that's the question. How many students in a class? There should be a class so that you have 6 students getting the same grade. So the lowest possibility for n is going to be 26, right? Because we are taking the roof here. Let's say some simple questions. A bowl contains 10 red and 10 yellow balls. So you have a bowl which has say 10 red balls and 10 yellow balls. Then the question is, how many balls must be selected to ensure 3 balls of same color? Yes, now we are slowly moving forward into this permutation idea. So one solution would be like you could consider the worst case. Instead, consider 2 balls of each color. You can't take another ball without hitting 3. Say for example, you have this bowl containing 10 red balls and 10 yellow balls, and often case it's when you choose these balls, it is the worst case scenario in which you might get 2 balls of each color and the third ball might be a different color. Yeah, that might happen. So generally speaking, your answer could be 5, and this is via pigeonhole principle. So if you look closely on what are the combinations that you come up with, if you just apply the pigeonhole principle idea, your answer would be 5. So the question again here, how many balls are required if there are 2 colors and one color must have 3 balls? How many balls are required if there are 2 colors and one color must have 3 balls? Again, you can have how many pigeons are required if there are 2 pigeonholes and one must have 3 pigeons. Can you relate to this pigeonhole principle? The same combinations you can use, and same idea, the theorem 2 you are using here to find the answer. Yes. A bowl contains 10 red ball and 10 yellow ball. That's what we have considered. And again, the question here is similar to the one we have seen earlier, the last slide. So you have 10 red balls and 2 yellow balls. You can't take another ball without hitting the 3 yellow balls. So that's where the answer is going to be 13 there. Okay, now we are going to have another sample questions in which we have 6 computers on a network are connected to at least one other computer. So this is kind of an application oriented question. So show there is at least 2 computers that have the same number of connections. Let's talk about the theorem here. The number of boxes k is the number of computer connections that we have here. So it can be like 1, 2, 3, 4 or 5, because among the 6 computers, 6 computers can be termed as 6 nodes. So there probably you might have like at least 5 edges. So you have 5 there, and the number of pigeons, that is n, that is the number of computers. So you have 6 in this example. You have 6 computers, that's like 6 pigeons. But generalizing the principle of pigeonhole, you have n by k objects. So then that's like 6 by 5, that yields you 2. So in other words, at least 2 computers must have the same number of connections among these 6 computers. So now we are zeroing in to this problem of pigeonhole. As we zero in, we move forward with different questions here. So if you look at these questions, consider 5 distinct points of x and y in the xy coordinate with the integer values of I varies from 1 to 5. Show that midpoint of at least one pair of these 5 points also have integer coordinate. So let's look for the midpoint of the segment a comma b to c comma d. So the midpoint we can say a plus c by 2 or b plus d by 2, because we talk about the midpoint, you just take that middle value or average. So if we can note, the midpoint will be the integer if a and c have the same parity and are either both even or both odd, right. So we talk about integers, we don't want to have a fractional value. So same for b and d, and there are 4 parity possibilities: even, even odd, odd, even, odd, odd. But if it's both even and both odd, you have more possibilities. That's what we talk about. So since we have 5 points, by the pigeonhole principle there must be 2 points that have the same parity possibility. So in our midpoint, 2 points will have the integer coordinates, generalized form. Well, now we come to this permutation and combination. As we just discussed about the pigeonhole principle, permutation and combination both are ways to count the possibilities. But for example, the difference is whether we order them or not. Yes, for example, we will consider the permutation initially. Let's see, you have ace of dice and 5 heart, 3 clubs, claver 3, and 10 spade, k spade. Is that the same hand as k spade, 10 spade, 5 claver, 5 heart, heart of 5, and a dice? Well, it seems the order has been changed, but they are the same set of things. The question is, does the order the card are handed out matters? How it has been handed out, does it matter? If yes, then we are dealing with permutation. Yeah. If the order matters, then we deal with permutation. If no, then we are dealing with combination. So that's one of the basic difference that we have with permutation and combination. But basically both are used for counting the possibilities. Let's talk about the permutation first. Yes, permutation is an ordered arrangement of elements of some set S. Say for example, you have set S is ABC. So ABC, you have CBA is a permutation of ABC. You have different combinations you can come up with, like CBA, BCA, and so on. So OR permutation is the ordered arrangement of OR elements of the set. So you have in this example of ABC, you have 3 elements in the set. So if you want to have an arrangement of OR elements, like 2 elements of particular set, then you could say 2 permutations, for example. Let's talk about this. You have this cards with 5 cards, A of hearts, A diamond, 5 hearts, 7 claver, 10 spade, and k spade is a 5 permutation of set of cards you have. And in this, the notion that we are going to use is PNR. As at times people use different notions, but here we are going to use PNR to represent the permutation. As the poker hand has 52 cards in it, so we could say that P of n comma r, which is P of 52 comma r, that is 5 things that we talk about. So this is like n and r. So number of poker hands, again we have this combinations like P and R can be written as P of 52 comma 5, that is 52 times 51 times 50 times 49 times 48. So you can see the combination, and again you can see what happens here is like you have n times n minus 1 times n minus 2 times n minus 3 times n minus 4. So that's how it goes on. Again for poker, blackjack, you have 2 cards, so that is only 2, n and n minus 1. So the R permutation notion, we have P and R. So the poker hand with this combination, it goes on like this. P and R is n times n minus 1 times n minus 2 till n minus R plus 1. In other words, you could write it as in this form: n factorial by R minus, n factorial by n minus R factorial. So you can come up with different questions, and you can try to see the possible solutions for this kind of problem. So could you think of some questions where you can use these permutation problems? Say for example, how many different ways can 3 of the letters of the word bite are chosen and written in a row? So the question is, we have this word bite. So how many different ways can 3 letters of this word bite be chosen and be written? You want to choose just 3 words from this word bite, which has we are going to choose only 3 letters from this word bite, and the bites have the 5 letters. So that is something like P of 5 comma 3, right, because it has 5 letters, which is n, and R is 3, because I mentioned that we are going to choose 3 letters from this word. So that would be 5 times 4 times 3 times 2 times 1. It is like 5 factorial by 5 minus 3 factorial, so which is 2 times 1. So your combination would be 60. Right. So this is the basic formula that we have: n factorial by n minus R factorial. More on this R permutation. How many ways are there for 5 people in this class to give presentation? There are 27 students in the class. So then you have the possibilities. 27 is the n, and we just need 5%. So P27 comma 5. So that's 27 times 26 times 25 times 24 times 23. Well, that goes to 9,687,600. That's quite a large. Well, then there is more information about this permutation formula. There are n ways to choose the first element, that is n minus 1, and once you choose the first element, n minus 1 ways to choose the second element, n ways to choose the first element, n minus 1 way to choose the second element, n minus 2 ways to choose the third, and so on. So that's the part of permutation combination. So n minus R plus 1 ways to choose the rth element. So by means of this product rule, you get n times n minus 1 times n minus 2 times so on till n minus R plus 1. So that's nothing but the actual formula that we come up with. So permutation versus R permutation. We know that whenever we choose a particular numbers from a given n, then that's where the R comes in. choosing an ordered phi card in the hand of P of 52. So generally speaking, when people say permutation, they almost always mean OR permutation, because we always talk about phi cards among 52 cards, three letters among the phi letters in that word. Choosing an order for all 52 cards is just 52 comma 52, which is 52 factorial. Right. Let's say, for example, let's talk about this question: how many permutations of A comma B comma C comma D comma E comma F comma G end with A? So we are talking about this. So there are 7 elements there. The last character must be A. Since the last character must be A, we just can have the rest in a different order. So the last character must be A. That's the primary goal. So which means that the B to G, they can have any order before that. So we want 6 permutations on the set of B to G. So that's simple, like P of 6 comma 6, that is 6 factorial 720. And the question that we might come up with is like, why not P of 7 comma 6? Why not take some time and think about it? Try to analyze why it is not 7 comma 6. What happens? What happens to A? That's a hint. Combinations. What if order does not matter? We talk about ordered informations in the past with the permutation, whereas the combination, that's where the order does not matter. Say for example, you have this 2 things, like both are same. As you can see clearly, they are exactly same, and the number of OR combination of a set with n elements, where n is a non-negative integer, where OR lies between 0 and n. You can simply write it as, sometimes at times people mention in different way, n, c, r is a way of representing, but generally speaking in our lecture we just use c comma c of n comma r, or c and r equals n factorial by r factorial times n minus r factorial. Again, how many different poker hands are there among the phi cards? So that is the same formula, n factorial by r factorial times n minus r factorial. So that's where we come up with this 2,598,960 different poker hands. How many different initial blackjack hands are there? So we just talk about 2 cards, so with respect to 2 we are coming up with this different combinations. So generally speaking, this is the form of proof. Let C of 52 comma 5 be the number of ways to generate unordered poker hands. So the number of ordered poker hands would be 311,875,200. The number of ways to order a single poker hand would be just P of 5 comma 5, that's 5 factorial. So that's a kind of permutation formula, right? The total number of unordered poker hand is the total number of ordered hands divided by the number of ways to order each hands. So that's simply saying that P of 52 comma 5 by P of 5 comma 5. That's nothing but you got the answer, C of NR, that is C and R be the number of ways to generate the unordered combination, and the number of ordered combination is R permutation, or P and R. The number of ways to order the single one of those R permutation is P of R comma R, and the total number of unordered combination is the total number of ordered combinations, that is R permutation, divided by the number of ways to order it. So just like CNR can be written as PNR by P or R. So that's one of the simple proof that you have. You don't have to worry much about the proof. In fact, there is a lot other proofs for each and every formulas that we are going to use. Basically speaking, the two formulas that we have seen about, one for the permutation and one for the combination, these are the two formulas that you have to understand. And here what we see here is the combination formula proof is the relationship that an ordered and unordered pairs of possibility that happens here. So we can see the relationship between the combination as well as the permutation. So this is general formula, as you can see here, how we have developed a CNR from PNR. Can you see the relations there? Okay, just take a note of this formula and their relations. Coming to this big string, how many bit strings of length 10 contains exactly 4 ones. So find the position of the 4 ones. Does the order of these position matters? It doesn't. As we talk about this position here, 2, 3, 5, someone or the same as 7, 5, 3, 2. So that's the question is how many bit string of length 10 contains. So CNR, that is C of 10, 4, that's 210 bit strings. So with respect to the same thought, you can think of at most 4 ones. Before we talked about exactly 4 ones, how about at most 4 ones? At most 4 ones you can consider the possible combinations in which you have it can be 0, it can be 1, it can be 2, it can be 3, it can be 4. So at most 4. It cannot go beyond 4. So with this combination you have 386. More on the bit string, at least 4 ones again. We have at least 4, which means that it can go beyond 4. 4, 5, 6, 7, 8, 9, 10 until 10. So with this combination you have 8, 48. Okay, then an equal number of ones and zeros, that's another way to find the equal number of ones and zeros. So that is 10 of C of NR is C of 10, 5, that is 252. Let's simply speaking about this corollaries examples. So there are CNR, that is C 52, 5 ways to pick 5 card poker hands. And in the whole course I just assume that you know what is the poker hands. So because I am giving the examples of poker, generally speaking about the permutation combinations and probability, we always use certain examples like poker hands or coins and so on. Again, as we can see here, to pick up 47 hands, we have different combinations you can come up with. So they are equal. P of 52, 5 equals to P of 52, 47. Yes, when dealing with 47 cards, you pick up 5 cards to not deal, because we are not dealing with that. So as we talk about poker coin, we use the term deal. When you say deal, you are using it. As you can see here, as opposed to pick 5 cards to deal. So we use the term deals here. Let's talk about more on this combinatorial proof that uses counting. This again, as I told you, for the formula itself we don't have the proof. In fact, I am not going to ask you the proof. That would be out of scope for this class. So I am just giving you the informations. I am not going to prove it, and I am not going to ask you to prove it, because counting and probability and combinations and permutations are just part of this lecture. So I just skip through this 2 parts. You can have a look at this example. This is quite interesting examples about the circular seating arrangements of 6 people. When you form this circular seating arrangement of 6 people, first place the first person, say for example in the northmost chair, and then place the other 5 person. As you place these 5 persons, you come up with different rules that we have seen with the possible permutations of 120 ways to do this one. and alternate way you can also go for P of 6 comma 6, that is 720 ways to sit 6 person around the table. Initially we fixed 1 person at the northmost corner, and then you are going to fix for the remaining 5. But if you cannot go for this 6 person rotating chair, you have 720 by 6, that is 120 combinations. Again, this is the horse race. How many ways are there for 4 horses to finish if ties are allowed? Okay, again note that orders does matter here. Again, the solution, it depends upon the case. One is no tie, 2 horses ties, 2 groups of 2 horses tie, 3 horses tie with each other, 4 horses tie with each other. Because there are 4 horses, there is a possibility that 4 horses might tie, 3 horses might tie, 2 horses might tie. Again, 2 groups of 2 horses might tie, and there is no tie. With this you can see the combinations. Because there is no tie, then the permutation is just 4 factorial, 24, and there are 2 horses that is going to be tied. So you have this group of 2 horses being tied. So 6 ways to choose 2 horses tie, and again here 6 ways to choose 2 winning horses. Other 2 horses tie for second place. Here 3 horses being tied, so you use permutation with 4 ways there, and we use product rule for 8 possibilities of this case. And all 4 horses tie, then there is only one combination of this. By means of some rule, the just combination, you have just add up 24 plus 36 plus 6 plus 8 plus 1, so that is 72. Anyway, by means of this horse race, how many ways there are for 4 horses to finish if ties are allowed? So we came up with different cases and the solutions. And coming to this binomial coefficient, it allows us to do a quick expansion of x plus y power n, and basically this goes beyond our course, so I am just skipping this again. Basically when I say CNR or CNR, which means that n choose R, the notation that we use here refers n choose R. That is the thing that I want to explain here, and these are the formulas that we have been using it. And basically I gave you introduction to the permutations and general idea about the combinations. And in this part, especially in this part, I like to give you more notes, lecture notes. Apart from the video that we have seen here, I would like to give you some lecture notes that can help you to understand the actual things that is required for this course. There are some things that goes beyond the course, because the whole probability and statistics, permutation and combination is a huge area, and there is a limit that I want to set to this course, which will be noted to you during the lecture notes. So as I look forward for the next lecture, we will be still dealing with some polynomial combinations. Yes, as we go on to the next lecture, I leave you here and have a nice time. Until I see you, goodbye.